this next section is on major pesticide groups. You know, if we had a video that covered all the pesticides that are used, well, it'd be impossible to do that because there's literally thousands of active ingredient pesticides, so we can't possibly cover all of them. And even if we just broke them into groups, there's so many different groups of pesticides that it really wouldn't be possible to cover all the groups too. So what we've done here is we've taken the major groups of pesticides used in agriculture and outside of agriculture, and so we'll spend some time talking about them. We'll talk about what they do, what they're used for, talk a little bit about their toxicology, and we're going to focus in on the major risks posed by each one of these groups. And what we want you to do is from this point on, when you're using pesticides, of course we want you to have a good idea what the pesticide is used for. You're probably dialed into that. But you should also have in mind, hey, what's the greatest risk posed by this particular pesticide? Having that in mind when you're using the pesticide is a valuable piece of information. So we're going to go old school on you first. We're going to talk about some of the older pesticides. And you might recall that at the beginning of my talk I said that the era of modern pesticide use, it's less than 100 years ago. And amongst the first pesticides that were developed were the organophosphate and carbamate insecticides. So these two groups of pesticides, they're not the same, but they're related in so many ways. So we're going to kind of lump them together. So I'm going to give you a little pesticide history here. The organophosphates, and I'm going to call them the OPs, and the carbamates, that technology was first developed by the Nazis in the early years of World War II. So as you might guess, these were developed as chemical warfare. They were never used as chemical warfare. The war ended before the Nazis had a chance to use them. But that will give you an idea of their toxicity. So a little bit more background info. They were very commonly used in farming and general pest control. I mean around people's homes and wherever, from the 1940s and continuing on to the 1980s. Now, household use of these compounds is virtually non-existent, with just a couple of small exceptions, but they're still used in farming to a degree. But their use even in farming has declined dramatically since the 80s and 90s, and as we move forward, they're being used less and less. Now, one of the things about pesticides is that you have to look at them, both their goods and their bads. And these were excellent tools for pest control, particularly in production agriculture, and that's why they're still used to a degree. They're very toxic on their targets, and they break down relatively rapidly after applied. So that means you could use them on a crop like head lettuce. By the time you're ready to harvest that crop, those chemicals would have degraded and be gone from that environment. So the mode of action of the organophosphates and carbamates, they are CNS poisons. They're central nervous system poisons. And specifically, they're cholinesterase inhibitors. You might recall earlier in the video we talked about blood testing. These are the two groups of insecticides that if you're using them in farming, you're using them enough, you need to get blood tests. They're not commonly used outside of farming at all now, but still used in farming. They're toxic both to invertebrates, like insect pests, but they also have the same mode of action, the same toxicity risk to mammals, including humans. So they're mammalian toxicity, and you've got to understand there's a lot of organophosphates, and there are a number of different carbamates. They range in toxicity, mammal toxicity, from the moderately toxic all the way to the very highly toxic. Just to give you an example, early in my career I worked in the Salinas Valley here in California. It's a major vegetable producing area, and this goes back a few decades. And they were using methylparathion on vegetables at that time, and the methylparathion label says, this can kill you on your skin. So it gives you an idea of how risky these things are to handle. So as a group, though, these compounds, they range from moderately toxic to very highly toxic. So their most significant risks would be surface water contamination, these compounds getting in surface water, and then human and wildlife incidents, where humans were being exposed, perhaps farm workers were being exposed, or applicators were being accidentally exposed, or wildlife were being exposed, and there are actually incidents involving these. Examples of these would be malathion, which is not as commonly used anymore around households, but it's a lower toxicity organophosphate, so it's still available to you for use around homes for insect control. Parathion, kind of the very highly toxic cousin of methylparathion, or carbaryl or carbofuran. Our next group of insecticides are the synthetic pyrethroids. Now these are synthetic or man-made versions of a naturally occurring insecticide from chrysanthemum flowers. So this is a type of botanical insecticide, developed from flowers. The synthetic pyrethroids have been around since the early 1900s, but they didn't come in common use until later on in the century. In fact, in the decades since the 1970s and 80s, these synthetic pyrethroids have almost completely replaced the OPs and carbamates, certainly in a home use situation or residential pest control, and in agriculture to a degree as well. Matter of fact, if you looked at a graph of the decline in use of OPs and carbamates over the last few decades, you would see that steep decline in use, like in numbers of acres that are treated with OPs and carbamates. You would see that decline over the last couple of decades. You would also see an increase in the use of synthetic pyrethroids at the same time. So in a way, it's not inaccurate to say that these synthetic pyrethroids have largely or on their way to replacing the more dangerous OPs and carbamates. Looking at the words themselves, synthetic, of course, that means man-made. Pyrethroid, when you say that oid end of the word, that means a copy of something. For example, in science fiction, a fake human is called an android. I guess it's also a phone, but in case of science fiction, a fake human. So in this case, we're talking about a laboratory-derived analog of a naturally occurring insecticide from a flower. Mammalian toxicity, anywhere from slightly toxic down to practically non-toxic. So these compounds are still really good insecticides, but they're not potent poisons for most vertebrates. Most significant risks, off-target movement into water. These compounds used in landscape settings or agricultural settings, they can move into water. In fact, monitoring for them over the last few decades has shown some of these compounds showing up in urban waterways or other waterways on a regular basis. So they're used enough and used in a manner where they're getting into non-target waterways. The example I gave earlier about the insecticide accidental spraying onto pavement and then the sprinklers coming on, just that simple mechanism right there is a way that these kind of insecticides get into waterways. So if you, following the label of these synthetic pyrethroids, you're going to see don't spray them onto hard surfaces and make sure to not spray them before rainfall or irrigation. Some examples of these synthetic pyrethroids are bifenthrin, cypermethrin, permethrin. In fact, if it ends in thrin, it's a synthetic pyrethroid. Neonicotinoid insecticides. If you're looking at the name of the chemical, you see that word, it looks a little bit like nicotine, right? So neo means new, and oid again means a copy of something, or an analog of something. So these are copies or synthetic varieties of the nicotine molecule. So nicotine, found in tobacco plants, found in a lot of different plants in the nightshade family. Nicotine is actually a natural product in plants, and we believe that it's used for the plant to protect itself against grazing insects or animals. So it's a chemical warfare used by plants to protect itself. And we basically co-opted this strategy, and we're using them for insecticides. So the mode of action, these are central nervous system poisons, just like the synthetic pyrethroids and the OPs and carbamates, but all three of them have slightly different modes of action. They all work on the central nervous system, but all slightly different from one another. So that would be important for resistance development prevention as well. Mammalian toxicity, slightly toxic down to practically non-toxic. Most significant risks, impacts to honeybees. Over the last number of years, there's been a lot of research done on the decline of honeybee populations, a phenomenon called colony collapse disorder. And while researchers are not entirely sure about all the things that might go into this phenomenon, it's possible that these insecticides, in particular the neonicotinoids, might be involved at some level with honeybee decline. A number of different neonicotinoids that are used. Imidacloprid is probably the most common. Insect growth regulators. Now this is a completely different strategy. Instead of trying to kill the target pest with the insect growth regulators, what you're doing is population control. So these chemicals prevent juvenile insects from becoming mature, reproducing adult insects. Mode of action basically takes two flavors. The first one is the chitin inhibitors. The chitin is the material that the insect builds its exoskeleton, its hard shell, right? So these chitin inhibitors prevent the normal production of chitin and prevents the insect from developing from the juvenile to the adult stage. The other type of insect growth regulator is the juvenile hormone mimic. And this messes with how the hormones function in the insect, here again preventing the juvenile from becoming an adult. Mammalian toxicity, slightly toxic down to practically non-toxic. Potential impacts to non-target environment. Well, at least in theory, risk to crustaceans. Think of like lobsters or crayfish. They also have exoskeletons produced of chitin. So at least in theory, if these compounds were to get into water, they would pose some risk to these non-target crustaceans as well. At this point, we should probably talk a little bit about theoretical risks versus actual risks. And this also goes back to our formula, hazard equals toxicity times exposure. While the insect growth regulator, chitin inhibitor chemical, might have the toxicity enough to cause damage to lobsters or crayfish, there has to be exposure. So if you can keep those chemicals out of water that has lobsters or crayfish in them, there's not going to be an issue. Hazard equals toxicity times exposure. Some examples of insect growth regulators are hydroprene, methoprene, and pyriproxyfen. Let's switch gears and talk about herbicides. We're going to break the herbicides into two groups, the pre-emergent herbicides and the post-emergent herbicides. With the pre-emergent herbicides, they're used to provide long-term weed control, and in some cases used to prevent all plant growth, so basically producing a bare ground situation. Maybe you've got a utility yard or a dirt parking lot or a roadside where you don't want any weeds to grow at all for an entire season. So these pre-emergent herbicides would be used in those settings to provide long-term control. There's a lot of different modes of action of these herbicides, but most of them focus on controlling the seedling while it's still under the ground in the pre-emergent stage. When it comes to mammalian toxicity for the pre-emergent herbicides, they run from the slightly toxic down to the practically non-toxic. The most significant risk of these pre-emergent herbicides is groundwater contamination. You might remember it earlier in the video, we talked about groundwater contamination, and we identified the pre-emergent herbicides as the kinds of chemicals that have the properties, the physiochemical properties that cause the potential for groundwater contamination. There's a lot of different pre-emergent herbicides. Examples would be dithiopyr, diuron, isoxaben, simazine. Let's talk about post-emergent herbicides. Now, here again, just like with the pre-emergent herbicides, there are a lot of different post-emergent herbicides. So let's make sure we have the terminology correct here. When we say post-emergent herbicide, we're talking about an herbicide that's applied, that's sprayed, after the weed emerges from the soil surface. So it's post-emergent. Used in a wide variety of settings, both agricultural and non-agricultural. While most of them are translocated, and what that means is you spray the herbicide onto the foliage, and the herbicide gets into the plant and travels down to the roots, so it's translocated or moving into the entire plant. Most herbicides we use now are translocated types. Some are still contact herbicides. The best analogy for a contact herbicide is like a flamethrower. You spray the herbicide you spray that contact herbicide onto the target weed, and it burns the plant up. As far as mode of action goes, there's a lot of different modes of action for post-emergent herbicides. All of these, though, affect plant physiological or biochemical processes. Now, that's an important point because what that means is the major impact toxicologically on the weed has to do with things that only plants do, like photosynthesis or cell wall construction. Because animals don't have cell walls and because animals don't do photosynthesis, it's not as likely that they would be affected by the mode of action of an herbicide. Mammalian toxicity, just like with the pre-emergents, slightly toxic to practically non-toxic. Now, probably the most significant risk of the post-emergent herbicides is drift, the movement of the herbicide from the intended target area to non-target areas, particularly if that non-target area involves plants, nearby crops, nearby landscape plants, that type of thing. Now, there are a lot of different post-emergent herbicides. Some examples would be 2,4-D, aminopyralid, glyphosate, and triclopyr. Fungicides. Fungicides are a type of chemistry we use to prevent plant diseases. In particular, the fungal type plant diseases. The majority of plant diseases are caused by fungi. Some plant diseases are caused by bacteria. Others might be caused by viruses. In this case, we're just going to focus on the fungicides. So there are various types of fungicides, but we're going to break them down into two groups, protectant type and systemic type. The protectant type fungicides often inhibit things like spore germination. Fungi produce spores, so the protectant fungicide would prevent the germination of the spore, prevent the development of the disease by preventing spore germination. They're usually not too effective after the plant is already infected. The second type is called a systemic type fungicide, and these are translocated or systemic in the plant. They may move through the plant's tissue into the vascular system and inhibit fungal growth. So these might be used later on after the disease symptoms start to show up. Fungicides are not particularly toxic to mammals. They range from the slightly toxic to practically non-toxic. When it comes to the most significant risk posed by fungicides, though, it would be off-target movement into waterways. Some fungicides actually have a higher toxicity to aquatic organisms like fish or aquatic invertebrates. Examples of some commonly used fungicides would be azoxystrobin, betamil, and copper. Next, we want to talk about the anticoagulant rodenticides. Now, as far as rodenticide tools that are used, the anticoagulants are probably the most commonly used by homeowners and in residential pest control, and perhaps in agriculture as well. There are two different types of anticoagulants. The first generation, and we're going to call those the outdoor and indoor use, and the second generation anticoagulants that are indoor use only. Now, the mode of action of anticoagulants is they cause the target animal to bleed to death, to hemorrhage, after they consumed the anticoagulant bait. As you might imagine, the mammalian toxicity for the anticoagulant rodenticides is high. Their most significant risk then would be non-target exposure to pets and wildlife. Now, looking at the first generation compounds, they're not as risky for pets and wildlife. They tend to be less toxic, and they tend to last for briefer amounts of time in the bodies of poisoned animals. So think of it this way. If you kill a ground squirrel with an anticoagulant, and it breaks down quickly within the body of the target, let's say that ground squirrel, and your dog comes and eats that ground squirrel, that's secondary toxicity, right? So the primary compounds, the first generation compounds, they break down more rapidly in the body of that ground squirrel. Second generation compounds, those are the ones that are more toxic and last longer in the bodies of the poisoned organism. Examples of anticoagulants include warfarin, chlorphacinone, and brodifacoum. So we've now finished our final session on major pesticide groups, and it's time for you to take a quiz. Good luck.